So we can generalize now. If we've got a displacement time graph, we can always get the gradient to be the velocity. So if there's no gradient, there's obviously no velocity. If you think about it, if displacement was there and time is over here, if the displacement doesn't change at all, it stays the same value, the object's not moving. If, however, we are increasing our displacement in equal little intervals, we land up with a constant velocity. If, on the other hand, our gradient is going from gentle to steeper, we have an increasing velocity, and if it starts off steep and becomes more and more gentle in a displacement time graph, we have got a decreasing velocity. If I would like to find out the instantaneous velocity at a point, I will put that point down and then I will draw a tangent to the curve at that point and get the gradient of the tangent. If I would like to get the velocity when it's a constant velocity from a displacement time graph, I choose 2 points on the line and I determine my gradient. If I've got velocity time graphs, my acceleration is the gradient. The area under the graph is the displacement, and the area under the graph is also the distance. How does that make any sense? We'll try give you a few examples, but let's say I have velocity and time, and I go up and I go down and I do that. I have gone forwards, speeded up, slowed down. My displacement at that point, my velocity is 0. I have had to stop and I'm going in the opposite direction from that point onwards. So if I'm going in the opposite direction, I subtract that for displacement. So if it's distance, I add that area and that area together. If, on the other hand, I am dealing with displacement, I add that area, but I subtract this area over here, because in a velocity time graph, that is the opposite direction. Why? Because my velocity has decreased to a point of 0 and changed direction. So, if I have got a straight line over there, that means I've got constant velocity. All right, the velocity hasn't changed, velocity, time, and there is no acceleration. If my graph is going up like that with velocity time, my acceleration is constant and positive, and here my acceleration is constant and negative. Let's see how that applies to examples. So we need to take a look at this velocity time graph, and it's always on a straight road when we're dealing with these graphs because we deal with rectilinear motion. What specific change to the object's motion occurred at point D? Let's think about what has happened in this graph altogether. We have got an increasing velocity from A to B, constant velocity from B to C, decreasing velocity from C to D. At D, I've got 0 velocity. In other words, this object has stopped. And what happened immediately after that? It changed direction. Because we have gone below the curve, we've got a negative velocity. That negative means that I'm going in the opposite direction. What is the total time, if energy, where the object experienced 0 resultant force? 0 resultant force means 0 acceleration. And that means that I had to have a constant velocity. There is my area of constant velocity. So it is going to be between 10 and 30 seconds. So it is for a time of 20 seconds. Calculate the total distance covered by this object. So it's not in 11 seconds, it's in 50 seconds, the whole journey of this. So what's going to happen is we're going to say, I've got a triangle, I have a rectangle, I have a triangle, and because it's distance, I will add this extra triangle over there. So I am going to say half of 10 times 2 . I then take the rectangle at 20 times 2, length times breadth, half of 10 times 2 again, half of 10 times 2 for the DE triangle. We add them all and we get 70 meters altogether. Calculate the object's acceleration during the last little bit over here. Well, it's the same as this whole bit because it's constant acceleration from there to there. So I'm going to say change in velocity, and my velocity is final minus 2 minus another 2, final velocity minus initial velocity, and I am going to divide that by my change in time, which is going to be 50 minus 30, and I land up with negative 4 divided by 20, and that turns out to be equal to negative 0,2, and it's meters per second squared. Don't forget, it's an acceleration. Now we're going to have to, on a set of axes, draw a displacement time graph that represents the same information, and we have to clearly distinguish the 4 sections of the graph. So the first thing we're going to do is give ourselves some axes. We're going to label this side displacement, and we're going to say that that's in meters, and our time is in seconds. We're then going to say, starting at 0, let's go to 10, then 20, 30, 40, and 50. For the first part of the journey, we have got an increasing velocity. How do I represent that? I have a bendy curve. That would take me for the first part up until B. So that's this A to B section. Then I have a constant velocity for another 20 seconds till 30. So I'm going to go with a straight line until 30. That's that part dealt with. Then this object is going to have a decreasing acceleration until it reaches a point of 0. And that means that it is flatlining over there. After which the object turns around and comes back on itself. So its displacement goes the other way, and it is speeding up in the opposite direction. This over here is negative velocity, but it is speeding up in the opposite direction. The negative sign really just means the opposite direction, which means I come back on myself in displacement. Let's try another example. Use the following information in order to draw a sketch velocity time graph for a car moving on a straight horizontal road. Show your calculations and label key values. We're going to start at 20 meters per second, and during the first 40 seconds there's no acceleration. They've told me quite clearly that this needs to be a velocity time graph, and velocity is measured in meters per second, and time is measured in seconds. So we start at 20, and we go for that for a whole 40 seconds, and it's a constant, there's no acceleration whatsoever. From 40 all the way through to 90 seconds, we are going to have uniform acceleration of negative 4 meters per second squared. Where's that going to leave me by the time we get to 90 seconds? We're going to have to do a bit of a calculation over there. We're going to say acceleration is equal to final velocity minus initial velocity divided by time. The acceleration is negative 0,4. The final velocity is, I don't know. That's what I'm hoping to find out, so I can put something onto this axis. My starting velocity is 20, and my time is from 40 to 90 seconds is 50 seconds. So when I go 20 divided by 50, I find that this velocity turns out to be 0 meters per second. So in other words, this line goes down and it meets at 0. What is the state of the motion of the car at 90 seconds, it has actually stopped. We've just worked that out. 90 seconds, I'm stationary. My velocity is 0. By using the graph only, determine the distance travelled by the car during the first 90 seconds. With a velocity time graph, if I get the area under this graph, I will be able to know what the displacement or the distance is. It's going to be the same here because all the time I'm above the graph, so I'm in the same direction. So I am going to say, I'm first going to get the area under the graph, and the area under the graph is going to be equal to a rectangle plus a triangle, which is equal to 20 times 40 plus a half of 50. Remember, the base of my triangle is only 50 and my height is still 20. And I find that I get 1,300 meters. So that is how I would calculate the distance. And then they want a corresponding displacement time graph for those 90 seconds. So what I'm going to do is I'm going to draw up my axes, displacement, and the displacement is in meters, and my time in seconds. And again, I need to show my 40 and my 90 because they are key points. We don't always necessarily need to calculate every detail of the thing. We've got a constant velocity here of 20, so I go straight up. Constant velocity on displacement time graph is a straight line, and after that I have a decreasing velocity, so it curves like that till 90, and at 90 I'm horizontal because that's where I have stopped. What is my displacement after 90? I've calculated that, so I should label it 1,300 meters.